Welcome everybody. My name is Andrew Nagy, and you're going to have the next 2 days or 2 afternoons with me to learn CBRS and private LTE. So thank you all, number one, for registering for my session. Hopefully you're on the cutting edge like we are at Salona with new technology, new wireless for enterprise applications, and it'll be very informative and a good time the next 2 days. So a couple of housekeeping items before we get started. There is a sign-in sheet circulating around. Make sure you check your name off of there so we know that you attended. Ozar will be happy to mail out the materials that we go over the next 2 days for you. So as you're going through this material, it can, it's new technology for a lot of people. First introduction to some of these concepts. So don't worry about taking too many notes. All the material you see up here will be available to you, and we'll send it out later tonight. So you'll have it as reference. Today, why are we here? CBRS is new spectrum that's been opened up, and it's a good opportunity to learn it because it's going to impact a lot of people in enterprise wireless. So today we want to go over some theory concepts to understand CBRS and LTE as a wireless protocol, since most of us might be familiar with Wi-Fi instead. Get practical to understand how to design and deploy for CBRS networks with LTE. And then tomorrow we're going to dive in and do some actual hands-on. You're going to get some experience. We've got a lot of iPhones that we've brought with us. You get some hands-on time with an actual device running on a private LTE network. And we'll go through some test scenarios so you can see how it works and kind of what some of the characteristics that you can expect out of it are. So today, expect mainly theory and understanding the protocols and the spectrum aspects. Tomorrow we'll dive in more hands-on. Today we're going to cover both CBRS and LTE. From a housekeeping perspective, we'll probably take a break in the middle of the session somewhere as we break between those two topics. So you guys can go get coffee, get water, take a bathroom break, and then we'll come back and we'll dive into LTE. So hopefully you guys aren't too fried from other deep dive technical information that you've heard today, and you're relatively fresh to learn some new content because there's going to be a lot of it coming at you. So the other thing that I wanted to mention is I want it to be very interactive today. So as we go through this content, please raise your hand if you have a question. I would be more than happy to attempt to answer your question. I am a Wi-Fi person by background in enterprise networking. I'm learning LTE just as you are. I just might be a little bit ahead of where you are potentially. So I may not have all of the answers to your question, especially if you have a very deep technical question, but I'll do my best. And some of the deep content or questions that we get, we'll be able to answer tomorrow when our CTO joins us, who has a long history and experience in the cellular industry. So happy to take any questions as we go. Just raise your hand again so I can repeat the question for the video crew at the back. We are recording this session, so it will be available publicly at some point. I don't know the specifics around that yet, but just so you're aware, it is being recorded. So the agenda, so I talked about this, whoops, too far. Come on, backwards. Backwards. Okay. Wow, it really went forward. So today we're going to do CBRS, planning a CBRS network, and LTE. Tomorrow I will actually dive a little bit into vendor content. I'm with Salona. We manufacture a private LTE solution for the CBRS spectrum today. I'm going to go a little bit into our solution just so you understand how not only our solution operates, but also what some of the key characteristics are for cellular networks compared to mobile operator networks that you might be familiar with, because there are some differences in how they're architected and designed. And then we'll do the hands-on exercises. So, and then join us tomorrow night as well for the evening session. We're going to have a panel discussion with a few Wi-Fi experts and a few LTE experts from both sides to do a comparison of Wi-Fi and LTE from a technical and a use case and application perspective, so you can understand how the two technologies, what their strengths and weaknesses are, and how to position each one when you're looking at going into your customers' environments or in your own environment and looking at which technology makes the most sense for any given deployment scenario. We feel they're very complementary, and we'd like to have some time to discuss those comparison points. So let's dive right in. Let's get into CBRS, which stands for Citizens Broadband Radio Service. CBRS has been commercially available now since the end of January, and it is built off of LTE and upcoming 5G. So CBRS, when you think about it from a technology perspective, think of it like you think of spectrum bands for Wi-Fi. You have 2.4 gigahertz and 5 gigahertz for Wi-Fi. CBRS is really the spectrum band and the properties around that spectrum. It's not a protocol or a technology implementation per se itself. So on top of that spectrum, we either use LTE or upcoming here pretty soon in the next year or so, 5G. So just so you understand, there's a lot of confusion out there talking about CBRS networks, private LTE networks, just so you know the relationship there. CBRS is really like new freeway lanes. It's new spectrum that you have to increase your capacity in an enterprise environment, and it has a couple of key characteristics that you should be aware of. It has less interference because it's very lightly used today. The incumbents that we'll get into are very sporadic and very limited use throughout the continental US. The ecosystem has adopted LTE and 5G in the spectrum, so there's not really any Wi-Fi in the spectrum or other protocols operating. It's really all going to be LTE or 5G. And the FCC has set up coordinated use with what we call a lightly licensed model. That means it's shared spectrum, and there's a tiering structure to the sharing. So it's not completely unlicensed. You can't just go out and use it. You can't buy off-the-shelf components and just deploy one at home. So it's kind of a hybrid in between licensed spectrum, where mobile network operators pay a large amount of money for dedicated access to spectrum, and unlicensed, where anybody can kind of buy an off-the-shelf product and use it. So it's in between. You have to have an off-the-shelf, you have to buy a solution, but it also has to have not only FCC certification, but it also has to integrate in real time for operations with what we call a spectrum access system that we'll get into. And there's 150 megahertz available, and the channel sizes range from 10 megahertz, 20 megahertz, or 40 megahertz. Now, in cellular that we'll get into when we get into the LTE protocol specifically, we have a concept of component carriers, which is the size, the bandwidth coming out of any one radio or cell. And then we have carrier aggregation, which is kind of like wider channels in Wi-Fi, but it actually, in cellular, it aggregates multiple radios in a unit that overlap with the same sector. So in CBRS, we have, it's broken down into 10 megahertz channels as far as licensing goes. So there's going to be some priority access licensing as one of the tiers coming up, and that's going to be broken down into 10 megahertz channels. But the radios are capable of operating in 20 or 40 megahertz channels as well. And that's going to give us about 200 meg download and about 50 meg upload, best case. And the radio power levels range from 30 to 47 dBm, depending on indoor versus outdoor and some other characteristics. I don't know what's going on with this. Sorry. So timeline. This started back in 2010 when the NTIA put out a fast track report. They wanted to prep the market for introduction of new wireless technologies and to free up additional spectrum to meet the growing capacity demands that they were seeing in the market. And part of that, they wanted to open up 500 megahertz for new broadband initiatives. So this is where the seed of CBRS kind of came from, is identifying federal incumbent spectrum that could be refarmed or shared in order to provide more mobile broadband for consumer and private enterprises. In 2012, they built on top of that with the FCC put out a notice of proposed rulemaking on 3.5 gigahertz, which is the CBRS band, for small cells and spectrum sharing. 2014, they put out the rules from the FCC, and the WIN Forum started work in 2015 on the Spectrum Sharing Committee and the CBRS standards development process for this specific spectrum band. So really, the seeds started to grow there with forming rules around the spectrum in 2014 and 2015. In 2016, the CBRS Alliance was formed, which is more like a business alliance to promote the use of CBRS as a technology, and their other charter is to adapt LTE for use in this band, mainly taking LTE as it is and adapting it where necessary to meet unique business requirements for enterprises deploying in this specific band. The initial standards were published in 2017, and then just a flurry of activity between 2018, 2019, and 2020. So 2018, we have this concept that the FCC adopted for initial commercial deployment, which is kind of testing the water of CBRS. They didn't want to just allow it to start working. This is a very unique shared tiered spectrum with a shared cloud database and the spectrum access system. They wanted to test it out first before we completely open it up for commercial deployment. So ICD, or initial commercial deployment, commenced late last year, September of 2019. And that really allowed people to start using the spectrum on a limited temporary authorization basis. So you could apply to the FCC for a temporary authorization to deploy a CBRS network in a given facility or location, register it. The FCC would either approve it or deny it based on the characteristics in that location and of the testing you needed to do. And they were going to learn through that process through here early 2020. And hopefully through that learning process, we would find that things worked as anticipated and things worked well with the spectrum access system to protect incumbent users. And they did find that, so here in early 2020, they actually opened it up for full commercial deployment. So CBRS as a spectrum band is fully authorized now as of late January of this year for deployments. The phase we're in right now then is that we've got infrastructure manufacturers going to the FCC to certify devices right now. There's a small subset certified. A lot of other manufacturers are going and certifying devices in progress right now. And we have the 5 spectrum access system database vendors that are fully approved as of the end of January. They've been approved by the FCC that they're handling the spectrum grant process to protect incumbent users. They're handling that sufficiently. So that's what full commercial deployment means, is we're ready to go live, go through the certification process, start deploying networks as long as you're certified and integrating with the SAS. So it's still a very, very new technology, even though the seed has been kicking around since 2010 or 2012 with the band. Really, we've only had live deployments since September of last year, and very, very, 3 weeks into full deployment type of mode. What organizations should you keep an eye on in CBRS? There's 2 primary organizations. The WIN Forum. This is really a standards development organization, so think of it analogous to the IEEE for Wi-Fi. This is the group that defines the standards for the CBRS spectrum band. And then there's the CBRS Alliance, which is the business alliance to promote the technology as well as then to adapt LTE for use in the band. So CBRS Alliance is really more of a consortium of business-minded interests coming together, identifying business requirements, and adapting LTE where necessary with extensions in order to work in the 3.5, 5 to 3.7 gigahertz band. You have a question? So the question is there any interoperability testing? Yes, both on the WIN Forum side, they have certification of devices that to conform to integrate with like SAS. There's various protocols actually that for the coordination of the spectrum that the WIN Forum tests and certifies for. So there's like SAS to CBSD, and CBSD is essentially the AP component. There's SAS to SAS because all the various SAS vendors sync their databases on the back end. So there's a lot of protocols involved, and their certification takes that into account. On the CBRS Alliance side, they're also doing some certification, mainly for on-go branded certification, and that's more for the LTE side, that things conform to the CBRS LTE kind of unique features. So here's some of those certifications that I was just mentioning. So WIN Forum is, you're always one slide ahead of me, David. The SAS has a bunch of different standards that they cover. So SAS test specifications, CBSD test specifications, which is the AP side. The database, there's a PKI component for authentication, and there's various protocols for, again, the SAS to CBSD for spectrum grant and release. There's SAS to SAS protocols for the back-end database fidelity. And each one of those goes through a testing and certification process. The other one of note is that there's certifications for the ESC, which is the environmental sensing capability. This is how SASs kind of protect incumbent users. We'll get into a little bit detail of what an incumbent is and what they're doing in the spectrum. But the environmental sensing is in those areas where incumbents are operating, the SAS is mandated to deploy sensors to detect for the presence of those incumbent users, and then dynamically switch users off of those frequencies as required in those very specific areas. Question?
Can you define SAS?
Oh yeah, so SAS is Spectrum Access System. So it's essentially, there's 5 vendors. It's Federated, Google, CommScope, Sony, oh, and I always miss the 5th one. There's another one. Sorry if I forget which one it is. There's 5 vendors that have been approved by the FCC, and they maintain like this back-end database where every radio that operates in CBRS has to register with their system, inquire for what spectrum is available at a very specific location that device is going to be installed in, and then the SAS will grant them access to a slice of spectrum. And so this is a dynamic process, and we'll get into a little bit about how that works as well. And the other thing I should mention is, as part of attending this course, you are all also going to be able to go through the last certification aspect down here, a certified professional installer. And these are training courses that the SAS providers give to get certified to understand how the system works and to deploy particularly high power outdoor radios because you have to kind of certify that they meet and you're putting in valid data of the valid location, the valid power, antenna gain, azimuth that it's direction at, so they can tell the impact to the incumbents because they do some modeling on the back end as well. Question?
Who are the typical incumbents in the spectrum?
We're going to get to that. So hold off on that. The question was, who are the incumbents? We're going to get to that in just a little bit here. So from a certification standpoint, the SAS vendors themselves have to be certified that their sensor capabilities can actually detect the incumbent signatures. So if you're in Wi-Fi and you're very familiar with radar detection with DFS, for instance, this is analogous to that, but it does not operate the same way. So rather than have every CBRS radio dynamically sensing itself for radar signatures, the SAS is responsible for that on the back end. So they're deploying sensors out in those areas. You don't even have to worry about it. If the SAS detects it, they will inform the radios that are impacted through the SAS to CBSD protocol. So from that aspect, one of the things I talk about is DFS has sometimes suffered in the past in Wi-Fi with false positives and false negatives and things like that. Much higher fidelity from a CBRS perspective because they're out there deploying specific sensing that meets the incumbents, and like the DoD is one of the main incumbents, their strict requirements for fidelity of detection of those signatures. So you don't have to worry about it based on manufacturer's implementation.
So the SAS vendors are going to be deploying?
Yeah, so the question is, are the SAS vendors deploying these ESC sensor networks? And the answer is yes. Nothing that any end user partner, you don't have to worry about it. As long as you subscribe to a SAS and your equipment checks in with them for the spectrum grant and licensing process, you're covered. FCC Regulations, just a link so you know where it's at. It's under Part 96. So if you look at the FCC Electronic Code of Federal Regulations, you look under Part 96, which is about CBRS. So if you go to ecfr.gov, look for Part 96, you can read. The FCC requirements are actually pretty thin. It leaves a lot up to implementation, which is where the WIN form comes in and says, if I have to meet this FCC and DoD requirement, how do we actually go and implement that? So a little bit about that. Let's dig into the spectrum and the tiering structure itself. So there's 3 tiers to CBRS as a spectrum band. Tier 1 is the incumbents. Those incumbents include US Navy radar. So it's mainly shipborne radar when they come near the coastline on large aircraft carriers. And there's actually only 17, I've got it on an upcoming slide, there's like 17 aircraft carriers that could come in very specific coastal areas along the US. And so that's one of the incumbents. There's also, I think, 3 ground-based radar installations that could also be an incumbent. There's also fixed satellite service. So there's some satellite service organizations out there that have receive-only capabilities on this band at very specific locations throughout the continental US. Very, very specific. So the US Navy is kind of like a mobile, what they call a dynamic protection area, because those aircraft carriers can move and dynamically come into different areas along the coastline. The fixed satellite service is fixed. You'll know specifically if you're impacted in one of those areas, and you can easily avoid what frequency slice they're using in that area. The third one in the incumbents is the wireless service providers. We're not going to spend a whole lot of time on them. They're being sunset, so most of the wireless service providers that have use of the spectrum are being moved into the SAS kind of process and procedures as well. For most WISPs, that is happening this year in 2020. There's a few that are going to be grandfathered in until about 2023, but very, very limited use. So they're going to fall right into everybody else with the Tier 3 GAA that we're going to get to. Tier 2 is a priority access license. So a big focus for the FCC with CBRS actually was enabling 5G deployment across the US. This is a prime 5G target band. So what they wanted to do is they wanted to make it accessible for organizations, whether they be big or small, to try to get priority access to some of the spectrum for 5G use cases. And so what we see is they're going to have access to the lower 100 megahertz only. And we're going to get into some technical details because they can't use all of that 100 megahertz. So it's going to be auctioned on a county by county basis, and we'll get into the details with that. In any given county, only 70 megahertz can be auctioned off. So of the 150, you're guaranteed for GAA to have at least probably about 80 megahertz for use. And then Tier 3 is the general authorized access, which is essentially if the device is certified by the FCC and you register with the SAS, you can use the spectrum. Again, it's a 10 megahertz channel structure. And one other note about the priority access license, I mentioned in every county there's only 70 megahertz that could be auctioned. Any one bidder can only win 40 megahertz. So nobody can kind of consume all of the spectrum and just take it. And the reason, and there's a big backstory as to how the auction would happen. There's a lot of political maneuvering on the back end. Originally, it was based on census tracts. Then because of the whole 5G and operator influence, they went to a little bit larger area on a county by county basis. That way, operators that might be bidding, let's say, for large metropolitan areas like the New York City metro area, don't have to do it on a census tract because it wouldn't make sense for them to potentially try to deploy 5G on that small a basis. So there's some compromise there. But again, where we're looking at for most enterprise deployments is probably the GAA Tier 3. In rural areas, it might be cost effective for enterprises to start bidding on priority access licenses, but it's going to be dependent on what your use cases are and how much investment you want to make.
So I was going to ask, you might be getting into this, but who are the players to buy that?
Yeah, so the question is, who are the players to buy the priority access licenses? In the big metropolitan areas, it's going to be the large MNOs. It's going to be the Verizons and AT&Ts and T-Mobile Sprints of the world, right? Because they're going to see this as a prime 5G band to deploy, in those large markets. The price, per bit per megahertz is going to be really high in the metropolitan areas. The price is going to be much lower in the rural areas, which might make it, affordable for enterprises or managed service providers or WISPs to try to buy some of that spectrum. Question?
So RF doesn't exactly adhere to county lines. How are they kind of managing that overlap?
So the question is, RF doesn't adhere to county lines, right? So if you buy a priority access license, you have exclusive use of that license in the county. Neighboring counties, they're going to potentially be able to use this auction off the same spectrum. Through the spectrum auction process, again, it's 100 megahertz, but only 70 megahertz out of that. So my anticipation is that they'll try to stagger them a little bit in between counties so that, maybe this 70 megahertz doesn't completely overlap with the next county, so that there's channels that you can use like maybe on the edges or something like that. That's a good question, though. The other one is that the priority access license holders still have to go and integrate with the SAS. So they don't know specifically which 70 megahertz they're going to get access to. They're just going to get access to a chunk of spectrum that they've bid on. So they can try to buy up to 40 megahertz. They don't know which specific 40 megahertz. The SAS will still handle that dynamically.
Okay, so that is dynamic.
It will be dynamic, yep. So the anticipation there is then that radios that are deployed along, let's say, a county edge and other radios along the neighboring county edge, the SAS will handle that, determine the optimal frequency assignments for those radios, because they have sophisticated modeling on the back end. They use a couple different modeling kind of algorithms that they'll go through. And when those devices register, they'll go through the modeling process and determine what the best frequency assignments would be. I think this is getting stuck. I'm going to just use the keyboard. Okay. So how much is 150 megahertz? Because we have this question come up quite a bit is, well, it's not nearly as much spectrum as I have in Wi-Fi. What can I really do with it? A couple things to think about here. Compared to what licensed frequency is out there for big mobile network operators today, and 150 megahertz is actually quite a bit, especially since it's in what we call mid-band spectrum, which is good RF propagation characteristics and attenuation characteristics for high-speed mobile broadband. It's more mid-band spectrum than most, or actually all of the licensed carriers have today. And then the other thing that we'll get into is when we get into the LTE topics, we'll understand how frequency reuse happens in LTE that makes it, higher efficiency than potentially Wi-Fi, and you can get greater frequency reuse out of LTE. So you can actually reuse those channels more often without having negative interference kind of aspects. Yeah, question? No, I'm good. Oh, I'll be all right, thank you. So let's talk about the different tiers in a little bit more depth. So tier 1 is the incumbents. It's mainly shipborne and ground-based radar in very specific locations. So these are covered by what the SAS calls dynamic protection areas. Since the aircraft carriers are mobile, obviously, we don't know exactly where they're going to come in along the coastline. Yep. And so they're dynamic protection areas then because we have to dynamically sense through the ESC networks that the SAS is deploying when they come in range, which frequency slice they're using, and then get the CBSDs or the radios to switch channels to avoid interference. The protection is guaranteed or needs to be activated per the FCC within 60 seconds. So if an aircraft carrier comes in within, it's like 40 kilometers of the coastline, the ESC network will detect it and has to register that in its system within 60 seconds and start notifying the affected radios that are deployed out there to change channels. Really, there's only 17 ships at 3 main sites. Those sites are Norfolk, Virginia, San Diego, California, and Seattle, Washington. That's where the prime kind of areas are that might be impacted. But again, the red areas there show you that anywhere along the coast are required to be covered by that ESC network. And typically, the other thing to note is they're not taking up or not impacting a large amount of spectrum. The aircraft carriers are really only using about a 5 megahertz slice of spectrum. So when they do come in range, the ESC will detect which 5 megahertz section is being impacted, and then move the very specific radios in that DPA area that are overlapping with that 5 megahertz. So it's not like when they come in, you're going to get kicked off the entire CBRS spectrum or a large portion of it. It's really very specific radios that happen to be operating on the same channel that impacts that 5 megahertz. Yeah, question?
Can a tier 2 or tier 3? Or can a tier 2 bump a tier 3 if they're getting relocated and be allocated to other spectrum?
Yes. So the question is, does that impact tier 2 and tier 3? And the answer is the incumbents, yes, impact both tiers below. And if a priority access license holder gets kicked off a specific channel and that radio moves to a different channel, it would be within the PAL area, the lower 100 again. That's kind of why we can only assign 70 out of the 100. We got to, if they get hit by the radar, they need to move to some open spectrum. So they have, those other 30 megahertz within the PAL tier to move to potentially. And then if there's GAA that gets impacted, they would have to move as well. But that's what the SAS is there for through their protocols, to optimize that with the minimal impact.
So the SAS will actually tell them where to basically channels.
That'll be covered in the CPI training that you're going to have access to a little bit more in depth. The SAS will not necessarily tell the radio which other frequency to move to. The radio gets notified, and then it does a SAS inquiry. And the SAS inquiry is essentially the radio asking the SAS, okay, given my location, which spectrum is available? That 5 megahertz chunk will be taken out of that because it's been detected. And it'll tell you, you have options of these 4 channels, which one do you want? And then the radio can try to register for one of those open channels.
How often will it go back and try to reuse that channel that?
That's a question I don't know. So the question was, how often will it try to reuse that channel that got impacted by incumbent? I don't know what the timer is for not sensing the incumbent anymore and then reactivating the channel. I'd have to look that up.
And what's the behavior if the SAS is unavailable?
If the SAS is unavailable, the spectrum grant that it gives to the radios is kind of in perpetuity. So there is a heartbeat that every radio goes through to sync up with the SAS. And I'd have to look up that timer as well of exactly how many heartbeats can be missed. It's not super stringent. Right now, it's I think 24 hours on the SAS backend that you can operate on that grant without renewing it or by losing the heartbeat. So, but that's some of those standards that are still in flux. They've changed a few times, so I'd want to go back and verify exactly what that timer is now.
Andrew,
Yeah.
how is the location determined by the radio when it reports to the SAS?
The radio itself, like a GAA deployment or the ESD sensor?
Either.
So the ESD sensor they've deployed it, they know exactly where it's at.
That's by the
Yeah.
5 companies, right?
Yep. So yeah, for more generic deployments, that's part of the CPI certification process. Every radio needs to be tied to a geolocation. So indoor CPI is not required, but you still have to put in its location. Outdoor high-powered, it has to be, that's why you're certifying it as a certified professional installer, that it is in this very specific location. And there's a process that every manufacturer like Salona is developing for the system to be able to dynamically either look up GPS location, because a lot of LTE base stations have a GPS receiver component on them. They can sense GPS and register it automatically in the system. Or if you happen to be indoor and need to register the GPS, you could do that manually in the system as well.
Did you say indoor low power doesn't require CPI to do it?
Correct, yep, and we'll discuss that in a little bit, but there are 2 classes of radios. There's category A and category B. The indoor, well, it's roughly indoor-outdoor, but don't use that as a guideline because the indoor ones can be deployed outdoors. They just have some restrictions. It's mainly low power, high power. And the low power ones, which are meant for indoor deployments, do not have to be installed by a CPI. Just the high power ones, because there's greater risk with that.
Hey, Andrew, when you say
Yeah.
indoor high power, is it just like you're saying, or you have to select each CDM, or how does that work? If you're indoor outdoor?
Yeah, category A, category B is really based on power output capabilities of the device. So you're going to know when you buy a device if it's category A or B, because it's certified category A or category B at time of manufacture. So every device is certified for one or the other. And we'll get into what the power limits are in that. And think of configuration just like you would with Wi-Fi. It's a max. You can configure whatever you want below that. Question?
So indoor then, that means anybody can install indoor CBRS, just like anybody can install Wi-Fi?
As long as the device, so the question is, since indoor or low power doesn't require CPI, can anybody install it? The answer is yes, as long as the device and the solution that you buy has been certified and interoperates with the SAS. And you need to make sure that it can connect to the SAS. So if you have, One of the things we'll get into is since it's an enterprise network deployment, it's riding on an enterprise network that you're in control of. So if you have firewalls and things like that that block its integration with the SaaS, you would be out of compliance. So you still have to operate it in a compliant fashion, but you don't need to have a certified installer do it. Does that make sense? So this is an example of, one of those dynamic protection areas that could get activated if an aircraft carrier comes into the coastal area. So the ESD Sensor Network covers the coastal areas, and if an ESD sensor detects the aircraft carrier come in, it would activate one of these dynamic protection areas, or that activated protection zone in blue there. Now, the exclusion zone are just all the areas along the coast that are covered, so don't worry about that too much, but just know that it'll activate a zone potentially between 40 to 80 kilometers from where it detected the incumbent activity. 40 kilometer for the low power category A devices, and it'll activate it for up to 80 kilometers for the outdoor high powered devices. So again, outdoor high powered have more potential to interfere with the incumbent. It has a little bit larger area that it needs to take into account when moving those units to a different channel. So that concept makes sense. Any questions on ESC and dynamic protection areas? Okay. The other incumbents are fixed satellite services. So there's really only 35 or so fixed receive-only sites in the US. These sites are not protected by environmental sensing capabilities from the SAS. They're very stationary, they know where they are, so the SAS has those included in their modeling, and so they don't really need to dynamically detect when they're operating. They're just assumed to be operating in those areas all the time. And again, these fixed satellite providers have very specific, well-defined frequencies that they operate on. So again, it's very, very well-defined. When you go in for a grant, you're going to be able to get spectrum in those areas still. There's just going to be very small sections of the spectrum band that are excluded in those specific areas. The SAS does, through their modeling, compute aggregate interference. They compute in the modeling 150 kilometers radius out from these locations for co-channel interference, and 40 kilometers for what they call blocking interference above a certain power level. So again, SAS is just doing a lot of back-end sophisticated modeling. When you register your device, it needs to take into account how it's going to impact that fixed satellite between 40 to 150 kilometers, depending on what your output power is. Question?
Are those sites spread across the band, or are they generally more in the provider or the general access?
Yes, the question is, are those fixed satellite providers spread across the entire band or limited to a certain range? If we go back a couple slides, you'll see that the fixed satellite service is really mainly the only in the upper 100. So we kind of got this thing of all 150 is could potentially get hit by the Navy incumbents. The fixed satellites in the upper 100, the WISPs we're going to ignore, and I suggest you ignore for now as well. And the PALs are just in the lower 100. So, you can see there's multiple variables stacking up that kind of make it a little bit. This is why we have a SAS that's very well defined to be FCC approved for operation. They've got to kind of take different aspects into account for different portions of the spectrum. Okay, so this is my 2-second spiel on the WISPs aspect of the incumbents. FCC Part 90, which is what they're defined under, is sunsetting those. It's sunsetting most of those providers and moving them into Tier 3 GAA in CBRS by the end of this year. So I wouldn't spend a whole lot of time, if I were you, worrying about the WISP aspect. They're going to be sunset and gone, and they're just going to fold in with everybody else. They are, for right now, like for the next year, they're computing aggregate interference again to 40 kilometers out from those sites, but that's being sunset. So the question is, there a way to look up what those WISPs are? I'm not aware of a way to look them up. I'm sure they're registered somewhere with the FCC. I'd have to do some more research to figure out exactly which ones are where. All right, let's talk about Tier 2. So Tier 1 was incumbents. We've seen how they're protected. Let's talk about the priority access licenses. So the auction, again, I mentioned earlier, it's based on a county level basis. I just want to give you a flavor for why it's county level. The operators, like the Verizons and AT&Ts, lobbied very heavily to try to get these areas as large as possible. They started out very small on a census tract basis, but the carriers wanted them to be what they call a CMA or a cellular market area. So the FCC for licensed spectrum defines these cellular market areas that are very large areas that conform to how carriers need to buy spectrum, not only so that the government can get the most out of the auctions, but so that the carriers, and then when they invest in equipment to deploying their cellular networks, can cover an entire metropolitan area and beyond with the same set of spectrum. They don't have to get too complicated. So a cellular market area is actually a very large area that encompasses many counties. So what I'm showing you on here is that compromise was census tract versus CMA. They landed in the middle on county level basis. So this is the New York City area, and you can see the cellular market area covers the entire area on the left, but there's 17 counties in that area. So for CBRS, it's broken down into kind of a hybrid. It's smaller areas than typical cellular licensed spectrum, but it is big enough that they can try to get operators to deploy it on somewhat large-scale basis. The other aspect about the auction is that the winners for the county level auctions do have to conform to performance requirements. So there's some requirements. It's a 10-year term for the license. By the end of that 10 years, they have to have met some performance requirements like serving a certain amount of the population in order to keep that spectrum.
Is it just tier 2 that auctions, right?
So the question is it just tier 2 for the auctions? The answer is yes. Yep. So here's how the priority access license holders would actually acquire spectrum. They don't get very specific channels or frequencies. They get a certain amount of spectrum in the lower 100 megahertz, and they integrate with the SAS, just like everybody else in GAA Tier 3, and the SAS will grant them that amount of spectrum that they've auctioned off and licensed to that specific provider. So what you could have here is you could have contiguous or non-contiguous assignment of the PAL licenses to any given operator. So here you can see bidder A might have won 40 megahertz. The SAS will dynamically give them 40 megahertz in that band, potentially split up between two different areas of the lowest 10 megahertz and maybe the upper 30, for instance. And then bidder B might win the other 30 megahertz out of the total 70 that can be auctioned off in a county. And then they might get, some contiguous spectrum in there. This is not defined how it's going to happen. This is just an example that they dynamically still acquire specific channels just like everybody else. And so, yeah, the verbiage there is that the SAS will try to assign contiguous spectrum to the PAL license holders to the extent feasible. So if their algorithm determines that it's feasible in that specific location, they'll try to give them contiguous, but it's not guaranteed.
So that makes the bidder A and bidder B, it can change, they just have 40 megahertz of that, they don't have specific frequency.
Yeah, so the question is the bidder A, bidder B, the 40 megahertz and the 30 megahertz could change. The answer is yes. So if an incumbent comes in, they dynamically register, get a grant for very specific channels on radios. And it could be dynamic in that 100 megahertz. An incumbent could come in and they can still force them to move. So that's why they don't get very fixed channels. They still need to move if an incumbent comes in. Question?
Can there be second bidders or just?
So the question is how many bidders can win? I'm not entirely sure. I would imagine my assumption is that up to 7 bidders could win because they're in 10 megahertz chunks or channels. I'm not 100% sure though. My anticipation is that in larger areas, the operators are going to try to buy as much as they can. Based on an operator bidding level basis, they're probably going to win, like the highest level bidder, if they wanted 40 megahertz, will take it, and then the next one will probably take 30, especially in the large metro areas. In the more rural areas, if enterprises bid or WISPs bid and they only want 10 megahertz, 20 megahertz, you could probably have more than 2 or 3 or 4 bidders win licensing. Kind of TBD on how that shakes out with the license or the auction process.
So the extra 30 megahertz, which is dynamic, leaves room for the tier 1 guys, but it also leaves room for tier 3 operators.
So the question is, the extra 30 megahertz in the PAL block of 100 megahertz leaves room not only for the incumbents, but also for tier 3 GAA, and the answer is yes. So GAA users can use any of the spectrum that the PALs haven't taken. So the 10 megahertz chunks, those 3 that aren't taken in that band, can be used by GAA as well. And again, if an incumbent comes in, then they move. And if an incumbent comes in and let's say bidder A has to move off of one of their channels and they take one of those, then the GAA users, the radios that are in the interference area for the specific ones that moved could get impacted as well. So there's kind of a little bit of a cascading process there, yeah. But again, think of it as, an incumbent's coming in with 5 megahertz a chunk along the coastal area. So only one channel is likely to be impacted, and it's like geolocation zoned as well. So only the radios that would actually interfere then with where the PAL moved could cascade. So hopefully it should be narrow in scope.
But I can see in a large metropolitan area, like New York City or Atlanta or something, where your GAA user could get bumped off, basically.
So the question is, like in large metro areas like New York City, you can see where a GAA user would get bumped off.
Especially if,
So I don't want to overestimate it because the impact of the U.S. Navy incumbents is very, very minimal. It's very rarely that they come into one of these areas. Yeah. Yeah. So I mean, it's either well-defined in one of those 3 areas like Norfolk, San Diego, or Seattle, or it's going to be very sporadic. Or infrequent, I should say, not sporadic. Yeah, so again, it's tier 3 GAA then is, it's similar to unlicensed where it's licensed by rule. There's no auction process, you don't have to pay any money, but you do have to conform to the rules that the FCC has set out, and that means becoming certified with both FCC and WinForum. And the WinForum's that SAS integration components. So estimates on how much spectrum we actually anticipate being available for GAA and Tier 3. If a PAL is not deployed and active, you could use all 150. And so that's the requirement there is even after the auction date, which is going to happen next June here, if they haven't deployed radios on the specific channels that they've been granted PAL licenses for, you can still use it. So they actually have to deploy radios in that specific area on that specific channel before it would the SAS would not grant it to you. Once the PALs are auctioned and they've actually become live and they're deploying and they're out there, realistic use case is, we anticipate in most areas 110 megahertz still being available. Not all of the PALs will be deployed in a given county or in a given geolocation. A very conservative estimate is 80 megahertz of spectrum for GAA, assuming all the PALs have been auctioned and deployed in that location. And then the worst case is if you're in a DPA along the coastal areas or one of those fixed satellite service areas, you might have another 5 megahertz that on a channel that you can't use. So take 110 megahertz out of the equation and then you'll go down to 70 megahertz. So very, very worst case is you should have about 70 megahertz of spectrum to use. So when we get into deployment scenarios, some organizations say if it's available, let me use it. Other organizations are going to be more conservative and say, I want to plan for worst case. That way I never get impacted potentially. And so then that's kind of where the lay of the land is. If you're being very conservative, you might do 80 or 70 megahertz and just say that's still enough for my use case. I don't want any dynamic impact potential, even though it's very minimal risk. So I'm going to go ahead and just deploy on 70 megahertz. We're advising most customers through we're talking with their use cases and understanding where they fall on that risk scale and trying to, advise them properly.
How much would you typically use for like a small warehouse if it's just using things like scanners?
So the question is how much spectrum would you actually use for, let's say, a warehouse with scanners or something like that? Again, that gets into very specific application use cases. For a warehouse, I'm very familiar with warehouses. You could probably do it all on one channel if you wanted to, because LTE with the frequency reuse can allow that to happen, especially in low bandwidth environments. Higher bandwidth environments, you do want more channels to have the capacity and to spread out that frequency reuse, just like you do with Wi-Fi a little bit more. So it's really dependent on the application and that application's tolerance for bandwidth, latency, some of those performance targets. Was there another question over here? No? Okay. So let's get into the channel structure. Don't worry about the complex formulas there. I just wanted to put them up there so you know, have it as a reference when you get this material after the session today. You can find the frequency to channel mappings in a 3GPP spec, and that spec is in series 36, which is essentially the radio or the RAN access network specifications. So it's 36.101 is the tech spec for this. And the channel numbers are called EUTRA, absolute radio frequency channel numbers, ERFCN. It's a mouthful, don't worry about it. This is similar to your Wi-Fi channels 1, 6, 11, or 5 gigahertz, 36, 40, 44. What they do is there's this formula that maps the frequency to an absolute channel number, and the channel numbers span every band that 3GP operates in. So every unique band, every channel is very uniquely numbered, and so this is a global numbering scheme for all of 3GPP. So band 48 is CBRS. It falls into a portion of this table where they do the mapping from frequency to channel number, and that's the formula for you, where the variables there are, the low frequency is 3550 megahertz, and the offset or the starting numbering for this band is 55240. So the way that plays out then is here's your frequency to channel number mapping. If you're like me and you will not remember this or memorize it, you're going to have to print it out and remember this, just like you would. You've probably memorized Wi-Fi channels just using them enough. Once you use this enough, maybe you'll memorize it. Until then, keep the table handy. Since there's no real concept of static channel planning in CBRS, though, you probably don't need to know it if you don't have to. Just know, like when you're looking at stuff in a radio, what that number means, where it references to, and if you want to look up the mapping, you can. So the numbering actually happens on a 1 megahertz basis, but I've kind of condensed it down into 10 megahertz because that's the smallest channel width available for CBRS. So if you had 10 megahertz wide channels, that would give you 15 channels in the CBRS band. I've highlighted them in blue. Again, just like Wi-Fi, the conformance here is you reference the center channel frequency. So the center channel frequency for channel 55290, the top one on the left there, is frequency of 3555 megahertz. So 5 megahertz below, 5 megahertz above. If we look to 20 megahertz channels, then you would potentially have 7 20 megahertz channels available. This is one example because you can skew those channels to the low end of the band or the high end of the band because you have about 10 megahertz of wiggle room there. So if you're skewing it toward the low end of the band, these would be your channel numbers for 20 megahertz. Any questions on channel numbering? Yeah.
More channel reads. So is it like Wi-Fi that if you have, say, a warehouse with 3 CBRS access points, they're all going to be operating on a different channel? So the question's about frequency reuse. So if, let's say in a warehouse, you said, if we have 3 radios and they're all operating on different channels, more than likely, yes. What we'll get into is cellular's SON capability, which is similar to RRM, or radio resource management. It's called self-organizing networks. It's the process by which a manufacturer's equipment will determine through the SAS integration what spectrum is available and then allocate that to a system of radios for the most optimal configuration. You can operate LTE on a single frequency, which is definitely doable. Licensed operators do this all the time. And that gets into more of later today when we get into LTE and how the protocol handles interference. The short answer is, unlike Wi-Fi, it doesn't do preamble detection and backoff. So Wi-Fi is completely blocking. If I hear a preamble, I have to defer and wait. LTE does not operate that way. Number one, all the radios
have a sync process, and they can actually sync their frames in the time domain so they don't overlap, and they can schedule them so they don't overlap. And the other thing that they can do then, hold on, the other thing that they can do is instead of treating it as complete back off and deferral, they treat it as just interference as raising the noise floor. So it influences the SINR noise floor for a given transmission, but I can still transmit at the exact same time on 2 different base stations on the same frequency. They're non-blocking. I just might have a lower MCS data rate because my noise floor is a little raised. That gets into some more, very technical design parameters of where your sectors are, where they're pointing, where their sectors are covering, and how much noise that introduces. But just know it's non-blocking. So, and that's what we'll get into as well when we start doing network planning, as we'll see if I start ratcheting down how much spectrum I'm using to serve a given capacity requirement, that the number of radios to deploy does not scale linearly with how much bandwidth I have, because I can actually reuse that frequency more often than, let's say, I could in Wi-Fi. You still need to do some channel planning potentially, and the SON will try to take care of that dynamically in the system, but it's just, I would say, not as impactful as in Wi-Fi, if that makes sense. Question? The question is, can we expect a capacity planner from me? No, not me particularly. Salona has one that I'm going to highlight later on today in the planning section. We have a web-based tool that can give you a rough order of magnitude of how much spectrum you have available at a location and how many radios you need. We'll go into that.
So the frequency coordination and the time domain coordination of the spectrum is a TDMA variant.
Yeah. So the question is, the frequency coordination for interference in CBRS specifically, since CBRS uses TDD LTE, or time domain duplexing, it's TDMA, essentially that same concept, yep. But all the radios are syncing up through their EPS or, through the system, since LTE is more than over-the-air spec. LTE is the portion of the over-the-air spec. The other one is the EPS, or the Evolved Packet System, which is the packet core and all the control plane functionality and all that. It operates as a system, so as a system, it can sync those radios up to coordinate that in the time domain so that they don't interfere. Yeah, question?
So when you deploy CBRS, you check in with the SAS data, it tells you what spectrum is available. Is that the same for low power deployment as it is for higher power?
So the question is, when the radios at CBRS check in with the SAS for power levels, is that the same for low power and high power, category A and category B devices?
I assume if you're low power deployment, it doesn't really matter what's being used miles down the road.
Yeah, so both category A and category B are required to integrate with the SAS, request spectrum, and the SAS does modeling. So when what you're going to go into the CPI training when you get the voucher for that and go through that training, they're going to tell you what those specific requirements are and how the modeling happens. The modeling, so when the radios register with the SAS, they actually register not only their GPS location, they register their install height, their antenna gain, and azimuth, which is orientation, so that the SAS has all the data it needs to accurately model the RF propagation and impact. And the ranges that it models for indoor are less than the range for outdoor. So yes, it still does all the modeling for the indoor, and so it'll actually model indoor radio interference with, let's say, your neighbor as well, to understand what the best frequencies are to potentially allocate. And then from there, any given enterprise's SON aspect of their own infrastructure would then optimally delegate those radios out to the different radios, or those channels out to the different radios. So the interesting thing we'll get into is there's a concept of a domain proxy where not every radio has to check in with the SAS. It can be offloaded to a centralized element. In Salona, we implement our domain proxy in our Salona Edge, which is our packet core. So let's say you have 100 radios across this building. The domain proxy in the core is going to integrate with the SAS, know the specific location of every one of its radios it's managing, and each radio could have a different subset of that spectrum that the SAS is saying is available for it. So the ones on this edge of the building are next to a neighbor. That neighbor's already operating on these specific channels. So to avoid that, maybe you have a different subset available on these 4 radios than the 10 radios over on the other end of the building. So every radio will have a different subset of frequencies that the SAS will grant it, and that's the job of the domain proxy, is to optimally figure out what the best arrangement of those channels are for frequency reuse, non-overlap, and performance.
That's a customer-owned device, the domain proxy.
The question is the domain proxy a customer-owned device, and it's yes. This isn't, we're talking about enterprise-owned and controlled deployments. So for CBRS, by and large, it's either going to be the enterprise owning the radios and its own packet core and all the related systems, or it's going to be like a partner and a managed service provider that will own it and help the customer through that process, but completely controlled by the the enterprise or the community.
Do the radios use Ethernet as transit to the core, or is it some other proprietary transit?
Yeah, so the question are, do the CBRS radios use Ethernet as its transportation to the core or backhaul? The answer is yes. Most CBSDs or CBRS service devices, which are the radios, use either Ethernet, Cat6, or they use fiber. They're kind of like a cellular small cell, essentially, is what the terminology is from a cellular perspective. I have yet to see one that doesn't support one of those 2 methods. I mean, so the question is, does it work on an IP network, or do they have to be segregated? It's dependent on the manufacturer's implementation. So if, let's say there's an MNO, like Verizon or AT&T is coming in to try to sell you private LTE, they might want it completely dedicated, and they want to run their own fiber, they want to control everything, and just sell you private LTE. The Solona approach that, I don't want to, this is a vendor-specific thing, is we integrate with an enterprise's existing network. So our radios are just like Wi-Fi APs. They plug into your switches, they use your cabling, you plug in the packet core, which is the Solona edge, into your network. You have routing, you have firewalls, you have everything in between. This is really an overlay to your existing enterprise network.
How does the certified engineer do their planning to provide that information?
So the question is, how does the certified engineer do their planning to provide that information to the SAS? Yeah, so really it comes down to the technician doing the install doesn't have to be the CPI certified individual. The CPI certified individual is just the one taking accountability for the system. And that's really mainly for outdoor or high power installs. So there's a process that, again, going to be manufacturer dependent to make sure that you have correct GPS coordinates for every radio installed. Outdoor, more than likely, that's going to look like GPS units that are bundled into the small cells. Almost every small cell is going to be manufactured with GPS built in. It might look like a separate little antenna off the system. It might be an integrated antenna. Indoors, where GPS is harder to acquire the signal for, then it's going to be a manual or automated process within the manufacturer's specific system to assign GPS coordinates. So that could be a technician that has an app on their phone that can acquire the GPS signals and dynamically map it to a radio, or it could be manually putting it in the system somehow, or somewhere in between. It's pretty much implementation dependent.
In terms of design, though, how do you do the design to provide specs of
Oh, yeah. So the question is, how do you do the design for the CBRS radios? I'm going to get to that in a CBRS planning section just a little bit later today. We'll go through essentially predictive modeling as well. Well, we'll go through the Solona network planner for how many radios you need given capacity and location. We'll go into very specific predictive modeling, just like you're familiar with Wi-Fi. You'll do an install. You can also do a site survey afterward of live measurements. Very similar process to how you do it with Wi-Fi, just a little bit different technology underneath. Is there any other question? Yeah. Can you speak up a little bit? I can't hear you. Oh, if there's a quality service mechanism in this technology, yes. It's very complex. We're going to get into it later today in the LTE section. So I don't want to dive into it now because it can be a kind of lengthy topic. We're going to get to it though, yeah.
So it's technology dependent. So if it's LTE, it will be kind of LTE quality of service. It's something different.
So the question is it technology dependent? Like LTE, it'd be LTE's QoS. If it's 5G, it'll be 5G's QoS. Yes. So CBRS is just the spectrum. How you use it, what protocol you run over it, is going to be LTE today, 5G in the near future. And LTE has very well-defined QoS with EPS bearers and things like that we'll get into. 5G has analogous QoS mechanisms.
Yeah, regarding the Ethernet connection to the backbone, what speeds would normally be 1 gig, 1.5?
Yeah, so remember right now with CBRS, the question is what speed will we need on the backhaul? Remember with CBRS spectrum, the largest channel width right now is 40 megahertz, maximum about 200 megabits downlink and 50 megabits uplink. So today you don't need anything more than a gigabit Ethernet connection. Okay, so on the FCC side as well, some of this, licensed by rule, they have spectral limits that you have to comply by. So for the infrastructure side, or CBSD, it operates on a specific channel. What are the out-of-channel spectral emissions limits, and then what are the out-of-band limits? So within 10 megahertz of the operating channel, it has to reduce power output by 13 dBm per megahertz. Greater than 10 megahertz away from the operating channel, and it has to drop by 25 dBm per megahertz. So that's kind of the, you're used to the OFDM shape and spectral limits from Wi-Fi. This is very similar for OFDMA with LTE and CBRS. The further away you get from the operating channel, the lower the power output and emissions can be. End user devices, they're a little bit more flexible. So instead of within 10 megahertz of the channel and greater than 10 megahertz, it's based on the channel bandwidth. So client devices are usually cheaper quality devices. They can't conform to the same RF front end capabilities. So they allow them a little bit more latitude to have spectral emissions away from the operating channel. So for instance, if it's a 10 megahertz channel, it'd be identical to what the infrastructure requirements are. But for larger channel widths, they give them a little bit more latitude to have the power drop off a little bit more gradually.
This is part of the certification.
This is all part of the certification process, yep. So again, a geeky detail I like to throw into my presentations, just so you have it in there to know what the spectral emissions limits are. Architectural overview, so I got into this a little bit. So this is getting into the WinForum and how the SAS operates. So again, we have CBSDs that can integrate with the SAS directly, with CBSD4 here, for example. Then you have other CBSDs. Let's say if the architecture is that we're going to do it in an aggregated, centralized fashion. You could have a domain proxy running typically on like the packet core type of solution that aggregates a number of radios and integrates with the SAS for them on their behalf. And then we have the SAS to SAS interfaces, so the SASs on the back end have to sync up. So if I'm integrating with any one of the SASs as an enterprise, I'm not integrating, let's say, with all 5 of them. If I get a grant for a specific frequency or channel at a specific location, all the other SASs and all the other enterprises that are deploying have to know about that to compute the models correctly. So all the SAS vendors on the back end sync their databases. Right now, that's being done nightly. They have enhancements that are coming to do that in more real time. That's going to be a maturation process for the SAS vendors over time. And then the SAS vendors do the ESC as well that feeds into the system for the incumbent detection. So that's kind of what the integration looks like. As an enterprise, you really just need to think about the lower portion with the radios and the domain proxy functionality.
SAS vendor get a specific geographic area in the United States, or
So
kind of share amongst each other?
So the question is, are the SaaS providers geographically segmented? No. The answer is all 5 of them can operate. They can control any and all portion of that 150 megahertz. It's just a matter of each enterprise and each manufacturer, which SaaS vendor they partner with and which one they integrate with. And they're all required to sync up on the back end. So each SaaS knows about everything nationwide that gets registered. Question?
Us as an installer or enterprise, we can make the decision on which one we want to partner with?
So the question is, you as a partner or as a customer enterprise can pick which one you integrate with. More than likely, it's going to be bundled in with the manufacturer solution that you purchase. So the manufacturer is going to integrate, they're going to do the coding and development to integrate with one or multiple SaaS providers. So for instance, Solona integrates with both Federated Wireless and Google right now. So we integrate with 2. And if you bought our solution, it would come with the solution. So really, enterprises and partners probably don't even need to think about it. As long as the SaaS vendors are certified doing their thing on the back end, it really doesn't matter which one you integrate with, as long as it's, operating normally. Okay. So here's where we get to those CBSD categories. So category A is the low power, category B is the high power. Category A, no CPI requirement. Anybody can install it as long as it's certified and integrates with the SaaS. It does have some restrictions. You can use it indoor, or you can use it outdoor at less than 6 meters height. And it has a 30 dBm EIRP limit. So that is what defines a category A, is really 30 dBm EIRP limit, and if you're doing it outdoors, which you can, you're limited in height. Category B, the high power, a CPI is required for this. You can deploy it outdoors only. You're not to deploy these indoors. And it can have a much higher power of 47 dBm, which is 50 watts. So you think about it, between the transmit power and the antenna gain, you can potentially cover several kilometers outdoors with one single category B CBSD unit. So one of the big benefits of this is large outdoor environments that need coverage, or the density of a Wi-Fi deployment might not be feasible. This has much, much larger coverage range than Wi-Fi can outdoors. And then geolocation capabilities. So again, especially for outdoors, you have to put in the GPS location, or it has to dynamically register with the SaaS. It has to be plus or minus 50 meters in the horizontal and plus or minus 3 meters in elevation. So that's the accuracy requirement that it has to be able to achieve to integrate with the SaaS and determine its location. Yeah, question?
This might be a silly question, but since category A can be installed by a non-CPI, say they do outdoor that's 8 or 10 meters high, how is that regulated?
Yeah, so the question is if anybody can deploy indoor, if they do it incorrectly potentially, how does that get detected and regulated? As far as I know, that's an FCC enforcement action. So they would get flagged, detected somehow by, let's say, a neighbor that they're getting interfered with or something. And somebody would file a complaint with the FCC. The FCC might go out and investigate and actually fine you for non-compliance. The difference is, since you're not having a CPI, there's not an individual that is individually held accountable. It would probably be more at the organization level. When you get to outdoors, there's a very specific CPI. When you sign off on an outdoor, or a category, I should stop using outdoor, a category B CBSD, you put your name in the registration database, and you are personally accountable for that. So, when you go through the CPI course that we're going to give you credit for through Federated Wireless, just understand, if you're signing for a CPI, as a CPI for an install, you're putting your name personally to that. And the FCC could, come back for you personally for liability. So it's a very important deal, and that's why, it's very well-defined, certified installer process.
Well, Andrew, on category A, since you're buying some equipment and it's checked into a database, could there be some way to say, hey, I know this is sold to Sean, and Sean incorrectly installed it? Would there be some type of tracking that way?
So the question is, they're tracking on a device. Well, see, the thing is, if you're abusing the SaaS integration and falsely identifying its location, yeah, it's probably registered in the SaaS somewhere, but you don't know exactly probably where it's coming from. It would have I'm assuming there's probably a unique identifier that if you go and you can sense it, then you can look it up in the SaaS and determine it was, registered in the wrong location or the wrong power or something like that. I don't know technically how that happens on the back end, but it is uniquely identifiable as a specific radio and tracked to then what organization has that registered, yes.
Say, you sold me a serial number XYZ or something like that, and I can say, hey, look, this device over here is doing something. And then I would assume there'd be some type of recording back and say, hey, Solona sold the device to Sean's doing it incorrectly, let's check in on that.
Yeah, I don't know exactly the specifics of how that would work. But they do check in and register with the SaaS individually and uniquely identifiable. So the process, you deploy radios in the network and they register with the SAS, or that can be through a domain proxy. The process for integration with the SAS then is you deploy them, they inquire with the SAS for what spectrum is available in that specific location. The SAS returns the list of available frequencies for that radio. So that's that's called the spectrum inquiry process. So you're inquiring with the SAS what's available in my location. Then you have a a grant process. So through the grant process then, the radio or the domain proxy picks a very specific channel that it wants a radio to operate on. I go out and I do a grant request for that channel, and the SAS can either approve or deny that request. And then you can start operating on that channel if it was approved. So through the spectrum inquiry, you could actually get back a list of channels that are available. You pick one, and then you try to get a grant on it. If you've already done the inquiry, I mean, you should be able to get the grant. Technically, you could ask for a grant on a channel without doing an inquiry first and just like saying, I don't know what channels are available, but I just want this one. And then the SAS might deny you. Question was, do I expect that to be automated? Yes. I expect this to be automated so at the radio level, there's already firmware in almost every small cell that you could integrate the radio with SAS directly. From a packet core perspective, that's through the SON or self-organizing network. And many manufacturers are developing the SAS integration automated in their SON algorithms, yes.
So you said there's a mechanism similar to RF for this. How often might the channel change?
So the question is, how often might a channel change? Through SON, it's really implementation dependent. If there's any change in neighbors that they want to optimize around. Incumbent, probably fairly infrequently, but once it gets more widespread, it'd probably just be other people using GAA channels, and you want to optimize. So there's no real set limit. It's implementation dependent, I should say. In the early days, I wouldn't expect it to fluctuate very much, and I expect most manufacturers to probably put in some controls around that algorithm, say have it run every so often in my network. I'm going to skip that one. So other spectrum globally opening up. So in the US, there's also spectrum in the 3.4 to 3.55 gigahertz band. So NTIA is looking at the 100 megahertz directly lower than the CBRS band right now. So that's very interesting. So if that moves forward, then we could potentially have another 100 megahertz directly adjacent to the CBRS band. 3.55 to 3.7 is already available in Germany. The UK is looking at 3.4 to 3.6. It's a little bit different use it or lose it type of lightly licensed spectrum. And then we can also look at LTE and private LTE and 5G operating in unlicensed. So when 6 gigahertz opens up, it might be an opportunity to use some of that spectrum for private LTE as well. So as enterprises are deploying into the 6 gigahertz band, you could potentially say, I want a portion of the 6 gigahertz to be Wi-Fi 6E, and I want a portion of it to be used for private LTE, and you'd have control over, how you use that unlicensed spectrum.
So would that be with multiplier?
So the question is, would that be with multi-fire or a different protocol? Kind of TBD on that one. I don't know yet. Multi-fire is kind of dead in the water, so I wouldn't anticipate it to be multi-fire. I would anticipate it to be private LTE, just like CBRS, only without the SAS requirements, since that would be unlicensed spectrum. Carriers are going to look at it as LAA, so it's still a very political battle as far as how those protocols interact. But the good news is if you're deploying private LTE, you would control which channels you would allocate to which technology potentially, and so you would be in control of, segmenting those apart from one another if you wanted to. We talked about CBRS from a technology perspective. Let's bring it a little bit more practical, and let's talk about network planning for CBRS. So how do you do it? What tools do you use? What's that look like? So from what process do you need to go through? It's going to look very similar to Wi-Fi, actually. You're going to have your wireless coverage and capacity planning. You still need to do some planning up front to understand how much capacity, what your coverage area looks like, and how many radios you're going to need. You need to start thinking about, especially early days of this market, what devices you're going to use and how you're going to do authentication and SIM provisioning. And then you need to think about enterprise network integration requirements, since more than likely, if you're deploying this private LTE, it's going to overlay to your enterprise network. You need to think about cabling, switching, routing, firewall integration, all your usual stuff that you need to integrate with because it's not handled for you. It's not a separate segmented system. So what do we need to do for coverage and capacity planning? What are the important and critical factors? You need to know the location of the network, since, again, we talked about SAS quite heavily, and the requirements for that are geolocation. You need to know exactly where radios are being deployed. So the design is going to be different, not only because of the facility characteristics that you're used to, but also based on the very specific geolocation of the network deployment. You need to know what spectrum is available at that location, and you're going to base your planning around that. You need to know the facility type and the coverage area that you need to serve. So you need to understand what your use cases are, how much area you need to cover for those business processes or use cases. And then finally, all your capacity requirements of number of devices, what applications are they running, and how much bandwidth they need. And when we get into LTE, some of the interesting things are you might actually want to know more than just the bandwidth requirements of the applications. You might want to know its latency sensitivity. What are its thresholds for packet error rate before the application starts experiencing problems, because a lot of the targeted use cases are very mission critical use cases where applications have very well-defined or tolerances for packet error rate and latency. We can start to get into robotics, automation, things of that nature with mobile edge computing platforms and things like that, and we get into very strict application requirements that you need to meet. So I'm going to talk a little bit about the first step in this process, which is the network planning as far as a rough order of magnitude of what spectrum do I have available and how many radios do I need for my use case. Solona has a network planner that is out there free to use. Going to have you log into that here tomorrow actually and start using it, but I'm going to give you the URL and you can feel free to go in and play with it ahead of time. It has some core functionality that you should be aware of. You're going to put in a specific address or geolocation, and you'll understand it'll do a real-time spectrum inquiry for that specific location. So you know from the SAS vendors, being Federated and Google, which is the ones we're using right now, what spectrum is available in that specific location. That's a real-time lookup that network planner is going to do for you. You can put in square footage, or you can draw on a map the outdoor area, if it's an outdoor coverage model. How large of an area are you looking to cover? It does the SAS inquiry, and you can also do what-if analysis modeling. So again, earlier I mentioned if you're realistic versus more conservative or worst case use cases for how much spectrum you might have available. 150 best case, 110 we're thinking is more realistic for most environments. 80 megahertz available if you're in a PAL area where it's been fully deployed. 70 megahertz if all the PAL's been deployed and you're in an incumbent area. You can do some what-if analysis modeling of the SAS says I have 150 today. What if I'm planning for 3 years down the road and all the PALs are deployed? Maybe I want to model that for a more conservative 80 megahertz down the road, and I don't want to redesign later. You can model that in our network planner and say, okay, SAS told me 150 is available. What if I change it down to 80 megahertz? How does that change the equation? What's my model look like then? And then you should know on the back end, this isn't just simple math, based on spreadsheets or tables or something like that. We're doing sophisticated modeling on the back end that is actually discrete event network simulation and regression modeling. So we've done a lot of regression modeling for a lot of different facility types based on large data sets of hey, what does office environments look like? What do warehouse environments look like? What do shipping ports look like? So we've got a number of different regression models that have large data sets underpinning them that we do this regression modeling on. So you'll select a facility type, and that'll determine the RF path loss modeling that we do. That'll determine the topology, like height variation in the environment. We'll do RF link modeling. And based on how many clients you put in, we'll actually model them spread out throughout the coverage area that you've defined. And each one will get mapped to, for instance, what's the RSRP at that location, potentially, what's the SINR that they can achieve. And then with LTE, there's very defined mappings between SINR and data rates, which is actually tested and validated on most or almost all LTE chipsets by the carriers to make sure they meet performance standards. So there's very well-defined mapping in LTE between SINR and data rate that's achievable, and it's tested and validated to those thresholds. Correct, the chipsets actually measure, yep. So this is what the network planner looks like on the web page. Feel free to go hit this web page on a device if you want to and start playing with it. The only requirement is there's no login. You just have to submit your email to use it. So we won't spam you, we promise. You'll get once a month, I think potentially a Salona newsletter in your inbox just saying, hey, here's what we're up to. And you won't get anything more frequently than that. So go ahead, feel free to start playing with it if you want. And we'll do some you'll get some hands-on time with it tomorrow. We'll actually run through some example scenarios in the hands-on section and have you model a couple of different environments, both indoor and outdoor. But there you can see where you put in an address. On the right-hand side, it'll look up the spectrum and tell you what's available there. That's all interactive. You can check on the different green check marks to uncheck them and see, well, what if I have less spectrum once the PALs are deployed or something like that. You select a facility type from the drop-down menu, and if it's indoor, you can do square footage. If it's outdoor, you can do square footage estimate, or you can actually draw a zone on a map like I have here. Draw it on a map, and it'll actually compute the square footage for you. And you've also tied it to a geolocation, obviously. And then below that, what I'm not showing is there's some capacity planning of number of devices and their bandwidth requirements, both uplink and downlink, so we can properly model that. The uplink versus downlink bandwidth is important to model correctly because LTE is a scheduled protocol. So the whole channel isn't taken for uplink or downlink on a burstable fashion like Wi-Fi. It's scheduled transmissions, and there's a weighting algorithm in the scheduler that says I want 60% downlink, 40% uplink, and you'll have some control over that in a network deployment. We'll get into that a little bit later on the LTE stuff. It's called a LTE frame configuration profile. So the other thing to note is that the eNode B, that's the terminology for a radio, the number of radios scale with the available spectrum, but it's not a one-to-one linear relationship. It takes into account the capacity requirements and the modeling done on the back end on the system, as well as then the LTE interference, intercell interference coordination. It's a very technical term in LTE on how it handles interference. So with Wi-Fi, if you're familiar with co-channel interference, preamble detection and backoff, LTE IC-IC is kind of the terminology they use, and that is essentially the high-level view is that's where each one of them can transmit simultaneously, and they just have a SINR impact to one another, potentially dropping the data rate depending on how high that SINR interference is. So a lot more frequency reuse in LTE is capable, and we model that in the system as well. So what you'll see here is when we have a given capacity requirement for a use case, and then we start taking away spectrum, initially you might not even see your radio requirements increase because we can do the frequency reuse over that area and still avoid interference. Once we start having an SINR impact, you're going to have potentially lower MCS data rates for clients, and then you're going to have to start increasing your eNode B count to increase the capacity to meet those requirements again. There's a question? So the question is IC-IC limited to the eNode B, or does the client take advantage of that? LTE is a scheduled protocol. The eNode B, or the radio, controls both uplink and downlink transmission, and they control it completely. So the client, a lot of things are different than Wi-Fi. You don't need clients to implement things because it's controlled by the infrastructure. So kind of a different mindset to start getting into for a lot of these topics is just understanding that the eNode B or the infrastructure can actually control a lot of this without clients having to do anything.
eNode B is industry generic term, or is it yours?
eNode B is an industry generic term for LTE. It's called Evolve Node B. I'm going to get into terminology when we get to the LTE section. I'll have a page for you that goes through some of the terminology and kind of what they mean. eNode B, just think of it as a radio, an infrastructure radio. And again, how much spectrum should you plan for? We've covered that already. So here's an example. If I have a 10 million square foot outdoor environment and I'm modeling a very specific capacity requirement, right? So this is a capacity driven model. I'm having enough radios that are being driven by capacity that I could actually, if it was coverage, I'd need less. So I'm just saying I've put in enough capacity that, I've got increased density in radios to serve this capacity. What happens if I start taking away spectrum? So let's say, I started with 150 megahertz spectrum, and then I start saying, nah, I start going down, and I say, realistic is 110. I go from 150 radios required, 150 radios required to 155, and I've taken away 40 megahertz of spectrum. I've taken away almost a third of my spectrum, and I've only gone from 150 to 155 as far as infrastructure radios go. Again, because it's non-blocking interference, so I get better frequency reuse out of the system. More conservative use cases, if all the PALs are taken, or if you're in a DPA area with incumbents, again, you start to have that hockey stick effect once you get down to really low numbers of spectrum, because the frequency reuse just gets really, really tough to match for. But for most use cases where you're even conservatively planning for all PALs to be taken, there's not a huge impact into the number of radios you need to plan for. Potentially, 9% more radios, 10% more radios than you would otherwise plan for. So even if you want to be conservative, it's potentially you're talking about, customers and their budgeting and their worst case scenario. How much do I need to budget for? Well, let's go ahead and budget if all the PALs are taken, even though none of them are taken today, and I just need to increase my E-node count by like 10%. It's not dramatic. So just to give you a flavor of, what the planner takes into account as far as LTE frequency reuse and how that modeling is impacted. Don't expect you to understand, the depth of that, but just understand it's not dramatic.
Is there a negative impact from over-deploying radios, like you do with Wi-Fi, where you get less?
So the question is there a negative impact to over-deploying radios? I think you're getting at like management overhead just for beaconing and things like that. And so LTE as well is different. It has defined subcarriers and tones for control channel information that does not grow. It's not dynamic. So you can, as long as you don't have a capacity from a client perspective, density requirement that's killing your network, you can deploy as many LTE E-node Bs or radios as you want. It's not going to impact your capacity, because even if clients connect to all of those radios, again, they're all kind of synced up and they can avoid that interference as long as you're not saturated already. But it'd just be a waste of money from deploying infrastructure perspective. So what tools can you use? Well, CBRS is very new spectrum. There's not a lot of tools on the market to design for this. Solona as a company is partnering with IBWave. IBWave is essentially the standard for indoor cellular design and planning. They have support for the CBRS band already. They're adding to their component and parts database for specific radios and antennas as we speak. So you can do a predictive design and an RF site survey in IBWave today. And we'll step you through some of the tools and capabilities of it. The IBWave team is here this week, so if you want to go talk to them, I would recommend that. Jamel is around, and you can go talk to him and get more details on their solution. But this is a good tool right now. It may not be in your suite today, but if you're looking for designing for both Wi-Fi and CBRS moving forward, it has capabilities for both. They do 3D modeling. So this is a 3D model actually of this conference center. They've done this for the WLPC conference in years past as well. They've 3D modeled Wi-Fi in the environment. We worked with them to 3D model and plan for CBRS in the conference center. So here, they can work up a 3D model of the environment. You can see this is the RSRP, which is analogous to RSSI in Wi-Fi world, the signal strength at different, throughout the environment. So RSRP is receive power. Essentially, it's a dBm value for signal strength. Just like you think of it as RSSI you do today with Wi-Fi, even though RSSI used to mean, and by the standard means a scale of 0 to 100, we use it as dBm in Wi-Fi today. That's what RSRP technically is. So technically, we're not using RSSI the way it was defined. We've adapted it to analogous to what RP is in the cellular world. So it's just receive power. And you can see here, this is the model of the conference center. We have 2 eNode Bs as the circles on the map there. One is in the back corner of this room, which is the one on the left-hand side of the map. The other one is out by the lobby, which is the one on the right-hand side. And you can see the signal propagation through the environment. And this is predictive model, so this is not actual measurement. This is, we put in the blueprint, we've put in the walls, we 3D modeled it, and then this is what put in the transmit power, the antenna, gain and directionality and all that. And this is what the model says should be the coverage in those areas. So all of that capability there. The other thing to think about, and I'll touch on very briefly, is that when you're designing for cellular, you need to design for different RSRP values than you do for Wi-Fi. So in Wi-Fi, it's typical to design for, let's say, a neg 65 dBm everywhere. In cellular, that's more like a neg 90 dBm everywhere. Because our receive sensitivity at the resource block level in OFDMA, we can actually maintain a connection all the way down to neg 120 or neg 125 dBm. So for us to design, we're designing to about a neg 90 threshold typically, rather than a neg 65 threshold. So you'll see that reflected in the lower end limit. So the lower end, if you can read it down here, is neg 120 dBm. That's kind of where the cutoff is from the visual. Yeah. It's a 15 kilohertz subcarrier. I'd have to do an online calculator to look at what the noise floor is. Somebody want to pull one up? 15 kilohertz is much lower than a 20 megahertz channel. So like 20 megahertz is neg 101 dBm, right? 15 kilohertz for the smallest, well, actually the smallest resource block is bigger than 15. That's the subcarrier. I'd have to look it up. Oh, you're talking kilohertz though for potential. It's all based on the resource block sizing. So with the smallest resource block, I mean, it would go really low. I'd have to go look it up. I have some LTE information on the subcarriers and the resource blocks, and we can plug that into an online tool and see what the noise floor would be. But again, here, we're talking the next one, SINR. This is a little different than signal-to-noise ratio and Wi-Fi as well. Same concept, but we're taking interference into account. And remember how we talked about LTE's frequency reuse and intercell interference coordination, ICIC? We're taking into account interference from my other radios, raising my interference in SINR. So this takes into account the SINR from all my radios in my own network, not just the SNR from the noise floor given the channel bandwidth. So it's a little bit different because Wi-Fi, we're always talking about SNR, just the channel, the ambient noise floor. Here we're taking into account the interference from our own radios as well. So question was, what's this eNode B in the conference? What is it? It's ERRP. I believe it's 24 dBm output and a 6 dBm gain or dBi gain antenna. So it's around 30 dBi, I believe. Yeah, and just rule of thumb. I mean, I hate rule of thumb, but you're going to see larger coverage area off of a CBRS radio at a comparable power level than Wi-Fi, just because of the lower receive sensitivity. You can get a lot farther away from this unit and still maintain a connection. And that connection can still be fairly robust as well. The smallest resource block, I can still get through, a couple usually a megabit or two download still. Whereas Wi-Fi, your lowest data rate's in 5 gigahertz, like 6 megabits per second. I can actually go down to a lowest data rate in LTE, much lower kilobits per second if I needed to. And the other interesting thing about LTE from a planning and design perspective is that there's very well-defined SINR to MCS or data rate mappings for LTE. And these are tested and certified and validated before a carrier will actually put them on their macro network. So at this SINR, you need to achieve this performance level. And every client device is validated before carriers will put it on their network in that fashion. So by using CBRS and LTE, the enterprise network kind of gains because of the work the carriers do. So given a given SINR, you know to a fairly good degree of certainty what data rate a client's actually going to achieve, and you can plan for that. There's not quite the wide range of variability in performance on the client side like you see on on the client side in LTE like you potentially do on the Wi-Fi side. So again, it's just differences, right? So if I know the SINR from this previous planning, I can understand exactly what MCS and data rate my clients are going to get and what performance they can achieve.
How do the transmission data rates map out to actual application flow over the network?
Yeah, so the question is, how do the data rates map to actual end user application throughput? Yeah, that's a much more complicated conversation, quite frankly. I think we'll probably have to take that one offline. That gets into all the low-level details of LTE and how, what's overhead and what's control channel, and also the scheduler of like what client density you have and what the demand is. Because the QoS scheduler through priority can weight which clients through the EPS bearers, which is the QoS functionality in LTE, which clients get prioritized better than other or higher than others. So it's not a simple answer, I would say. And everything that you're going to Google out there, and if you Google this, you're going to find all the macro carrier estimates, which again are assuming, you know, macro networks that have hundreds or thousands of clients on them. And I even have one in LTE on a slide up here of, you know, if you're getting 600 megabits data rate and your average download is 60 megabits, you know, you think, well, that's horrible. I'm only getting 1/10, but you're sharing it with everybody else. So again, you got to temper what you Google for in LTE because you're going to get a lot of macro data that is more just what could I get as an average public consumer. The private side will be different. So after you've done your predictive planning, you need to plan to integrate with your network. So that means from both the radio, the Soluna Edge, which is the packet core functionality, and then the management or the orchestration layer, what touch points do you need to think about of integration into an enterprise network? So from the RAN side, you need to touch network infrastructure for cabling, what VLAN segment devices are going to go into, IP addressing, all of that. You need to touch into your security infrastructure. Tunnels are created between the radio and the packet core. We'll get into the LTE section what protocols are used, but if you're going across a routed network that has any security, you need to make sure you open up certain protocols for the radio to talk back to the packet core. The packet core, the Soluna Edge, or what we call the Edge, you know, you're going to talk about end user authentication, how you map SIMs to users, what traffic controls you have, what QoS policies you have for different groups and applications. From the orchestration perspective, you might want to tie in with the identity management to map SIMs to users in your directory structure and derive policy off of that. You can also potentially integrate with Radius servers as well in order to authenticate through the SIM, but then authorize what policy and access they have through a Radius system still. So you can actually bifurcate and say authentication is in the SIM infrastructure, authorization of what they have access to, then I look them up in Radius and map them or something like that. So again, potentially a lot of integration points depending on what that enterprise environment looks like. Just know it's just like Wi-Fi, a little. As far as integration, it's just a little bit different.
Is open authentication an option where you don't necessarily have to register?
So the question is open authentication an option? The answer is no. Everything has to have a SIM. It has to authenticate. By default, that would be SIM AKA. There are other like USIM technologies that can use EAP authentication and certificates and all that. So you do have a choice, but there's no concept of open or pre-shared key in cellular. So again, talk difference in use cases. You're going to have use cases for Wi-Fi that cellular can't handle, like just open networks. With Soluna, we do zero-touch provisioning. So essentially, our systems call back out to the orchestration layer. You don't have to put an IP on systems. You don't have to do anything other than make sure your infrastructure can allow them to call back to the orchestration layer, get provisioned, download their policy, and start operating. So really, it's really simplified compared to a carrier network. You're not manually configuring and integrating a large number of components. You've got a end-to-end solution where you can deploy a packet core, and you can deploy radios. They'll automatically register with their assigned packet core as long as you've defined the policy in the orchestration layer of this radio is at this site, handled by this core. We'll get into some more specifics of that tomorrow when we go through the Soluna solution. But just understand from a market perspective, the goal is to streamline the deployment so people don't have to be cellular experts to deploy the systems. Just like people don't have to be Wi-Fi experts to deploy Wi-Fi today, These solutions are completely different than how the carriers approach them. And so they have different business requirements that we need to meet. From a RAN deployment perspective, again, you can break it out. If not everybody doing a radio install has to be a CPI. You can have any company that you contract with go hang an AP, go install an AP, as long as you have somebody in the authority chain, whether that be the customer, a partner, a managed service provider, that is taking responsibility for that outdoor AP or high power AP and certifying that it was installed in the correct location with the correct power and all that.
Are we going to see carriers try and use CBRS for picocells like they do today for other bands?
So the question is, are we going to see carriers try to use CBRS for picocells and other stuff? I think once carriers start rolling out 5G, they're going to be doing some county-based PAL licenses for 5G for outdoor coverage areas. Penetration, like indoors from carriers, I don't think is going to happen very much. They're going to go after very large venues, like stadiums and stuff, probably, potentially. But they're not going to be, I doubt they'll be able to penetrate into any other locations besides those.
I mean, we'll ship you a picocell, you plug it in.
Oh, you mean like order your own?
Fill it in a coverage.
Oh, so the question is more like a femtocell type deployment.
Yeah, am I going to have employees of my institution show up with one that they're supposed to use at home?
Yeah, I can't really say what the carrier's business model is. I mean, they've kind of moved away from femtocells from a large, perspective. I wouldn't anticipate that to be a huge thing, but again, that's something I probably can't predict.
A requirement to pretty much be always online, always have activities, you have to go and check in periodically, go through those elements. Is there any other thinking any use cases where it's more an offline or partial?
So the question is, since it has to be online all the time to maintain the grant, the spectrum grant from the SAS, is there an offline mode or perspective? Right now, the offline mode is just for stability reasons, that you have a grace period before you have to stop operating. It's meant to be pretty much always on though, always connected to the SAS.
Cruise ship is not going to benefit from having CBRS radios on the ship.
Well, a cruise ship goes outside of U.S. territory, so.
Well, because that's the gray area already with.
Yeah.
Which regulatory ability to put a ship on.
Yeah, that question I can't answer. It goes outside of U.S. territory, then technically it's not CBR. It doesn't have to meet CBRS requirements. It has to meet whatever territory it's in. So yeah, unless I would think cruise ships in particular would be very tough to deploy CBRS given the requirements for precise location, because again, they're out there in the ocean where incumbents could be with U.S. Navy carriers. And if they're moving, they would have to check in and update that GPS location all the time. So I guess if you're talking like, if it's always real-time connected and updating frequently, potentially you could do it. But I don't know. Yeah.
Is the SAS global or US based?
The question is SAS global or US based? It's US based. CBRS is a US specific technology.
I'm sailing around the Caribbean on a cruise ship.
Yeah.
Like, I'm going to report GPS coordinates to the rest of the US, and SAS is not going to know what to do necessarily.
Yeah, I don't see that being a defined use case for CBRS, at least at this point.
Do you think any other countries will go?
Other countries, they'll jump on board with shared spectrum in some fashion. It's to be determined whether or not they match the CBRS regulations and requirements, or if they go their own way and just say we're going to do shared spectrum in our own way. Like the ones out there in Germany and the UK have already kind of done their own thing. They have shared spectrum, but it's different protocols, different requirements that they have to meet. So CBRS, think of it as a very unique use of the spectrum for the US. Shared spectrum will have potentially other requirements. So what you're going to end up having for private LTE solutions is, if I'm in the US, which spectrum bands am I using and what are those requirements? I'll have different software and algorithms maybe in the same system if I register it in a different country with different requirements. Just like you do today with Wi-Fi, you have to put in a country code or something like that. You may have to do for an installation of which country am I deployed in and what are the requirements I need to meet. But that's, this is future looking. This is all just CBRS based in the US right now. But I think in the next 12 to 18 months, we're going to start to see a lot of those other countries define their requirements, and we're going to start to see products integrate with those requirements and start to implement them. So a very valid question, but probably just not there yet.
So you think like the actual product, the radio product, would probably be similar or the same with different hardware switches or something?
So the question is, will the radio or the product be the same product, just have different capabilities depending on where it's deployed? I can't forecast. I would imagine so in order to, serve the most amount of, use cases in a given product. But it's really to be determined on what those other countries' requirements are and whether or not that's feasible to do within the same product set or not. Once they get defined, then we'll know. So let's say you take a small cell, a CBSD today in the US, it doesn't have to do any environmental sensing. That's all taken care of by the SAS. If another country comes out and says, no, every radio must do it, well, then the radios for the US probably won't meet the requirements for another country. You'd be looking at a different product. But if it's close enough that the products can overlap and still meet both use cases or multiple use cases, then I would think that would happen. Okay, so we've deployed our network. Then you get to the survey solution. We used IBWave as an example for predictive design. They also have a solution for CBRS surveying. They integrate with a lot of third-party tools because when you get into LTE, their tools integrate and survey for a lot of different 3GPP bands, licensed as well as CBRS. So in order to scan for those bands, their solutions typically require third-party tools in order to do the scanning all the different LTE bands, potentially worldwide. And they can also, with IBWave Mobile, pair it to Android devices and smartphones that support those bands and get the scanning data off of smartphones. On the right-hand side, I don't know if you saw Jamel on Twitter. He tweeted out, hey, what's this device I brought with me to WLPC? Any guesses? That was a PCTEL scanner that scans all of the LTE bands. So it's a dedicated scanner that you could buy if you don't want to pair smartphones with a tablet to do scanning. And that's what we use to actually scan the conference center. So there's Jamel. He's using his device, and that is what the walk test. So in cellular terminology, instead of an RF site survey, if you hear walk test, that's kind of what they mean. Is they're walking around, they're doing live measurements of what their coverage, SINR is, and actually gathering RF performance criteria. So there's a question on if there's a difference in received sensitivity based on the individual device and its manufacturing, right? I would imagine so. I don't know the answer offhand. I think, sensitivity is, they conform to more rigorous standard or testing than Wi-Fi does. So I think it's probably variable to a degree, but not to the degree that it is in Wi-Fi chipsets. Because remember, LTE chipsets are more expensive component-wise as well. They are a little bit higher quality, so they cost more. It's difference in market, right? Wi-Fi is very cheap componentry for the consumer market. Not very cheap, relative to other componentry. It hits a cheaper price point to hit mass market consumer, right? LTE has been a little bit higher price point, a little bit different componentry. So I would expect there to be some variance, but not as huge. Oh, with the SINR to data rate mapping? No, that's standard. If you hit this SINR, you need to hit this data rate or a very tightly controlled range of data rates. So there's less fluctuation, yeah. Yeah, I would say you can look at RSRP from a CBRS perspective. Do most of your planning off of SINR though. SINR is where the rubber meets the road in LTE. You don't really need to care about the RSRP as long as you're hitting a given SINR.
Like right now for Wi-Fi, we have to plan for LCMI. Is that still something that we have to think about for CBRS?
Can you repeat that one more time?
For Wi-Fi, we have to design around the least capable, most important device because a lot of the Wi-Fi devices.
I didn't understand that acronym first time.
Sorry, do we have to do the same thing for CBRS?
So the question is, do you have to design for the least capable device in a CBRS network? I would say no at this point. I would say you can pretty much assume most of them are a pretty tightly controlled performance profile, and that if you're planning for this smartphone, it's going to be the same as the other one. If you're planning for a router gateway type of device or a bridge type of device, they're going to have higher gain antennas as well. So I think you'd be fine. There's just not the variance there is from my perspective. I'd be happy to be corrected though. So ask that question again tomorrow when our CTO is in and see if you get a different answer. I think he'll tell you that that is just not a thing in cellular. They test, this carrier specifically tests for those performance profiles, so they don't have to have that variance. SIM models, I'm going to just breeze through these. There's a whole, you just got to get familiar with SIMs and how to provision SIMs. There's a lot of, the ecosystem right now from a CBRS perspective is actually fairly robust. It's grown quite a bit in the last 9 months or so. So smartphone platforms, you're looking at, I think I have them on here. Nope, next one. Smartphone platforms, you're looking at the iPhone 11, you're looking at the Google Pixel 3 and 4, Samsung S10, Note 10, S20. There's a lot of cradle point devices and routers, Sierra wireless devices, a lot of Ethernet bridges from like Multitech, a lot of point solutions for like video security like from Lanner, BEC. There's a lot of devices out there. It's a matter of mapping your use case to a device and mapping that also with potentially a customer's device lifecycle refresh. If they have devices that are not CBRS capable today, but they have a use case, do I want to buy an add-on device to bridge that, or do I want to wait for their device refresh cycle to get them into that ecosystem? And again, that's going to be a planning exercise of maybe you tackle a subset of devices today, and over time you're going to grow their private LTE deployment as more devices get life cycled or deployed.
What about eSIM options for Solana?
eSIM is on our roadmap specifically as a manufacturer, fully supported. I mean, everything just carries over from LTE. So if you're looking at just generically in CBRS, it can be a physical SIM, it can be an eSIM, it can be an iSIM, which is a system on a chip with a processor. Any of those are all supported, it's just the SIM protocol has to be followed.
Who generates the SIM then? Maybe enterprise or?
So the question is, who generates the SIM and manages them? An enterprise would at this point, because you're fully under your control as a network. As an enterprise. So within Solana, we developed our own subscriber management system where you can provision and deploy SIMs. Today for us, that's physical SIMs. On our roadmap and later this year is eSIM capability for deploying it onto an eSIM on a device, which is still hardware based on the device. It's just you have it on the motherboard on the device rather than a removable. So yeah. Physical SIM, eSIM, or iSIM. Today, we just happen to be physical SIM through our product development. Over the within this year, we'll have eSIM capability.
Does that mean the device has a SIM for CBRS?
So the question is, does that device? So the question is, does the device have a SIM for CBRS? The answer is yes. You have to have a SIM that is the credential to get on the network you want to get on. So just like you have credentials for a Wi-Fi network today, the SIM that you provision on the device has to have credentials for your enterprise network, which means your subscriber management system, whether that's bundled in with the network infrastructure or whether it's a third-party add-on system, which is fully out there and capable, you can go buy one off the shelf. It has to be your SIM that you've provisioned and your system can authenticate. The second question, integration and roaming with carrier networks, is a little bit longer term. The CBRS Alliance is looking into neutral host options. The problem is, from a standards perspective, it is fully capable. It's just integrating with a carrier's packet core and network for roaming. That's more of a business partnership for federated authentication, very similar to Passpoint and Wi-Fi. It's business relationship oriented, not technology oriented. So I'd say right now there's no solution on the market. There's no integration capability today because the carriers aren't really actively invested in that. There's a lot of momentum in the CBRS Alliance to try to bring those parties together to enable that functionality. So look for the CBRS Alliance to drive that from a business market perspective. But the technology and all the protocols and capabilities are there.
So the iPhones you have back there, you unplug and walk outside.
Yeah. So right now, what we're going to show today or tomorrow for a demo and you can play with is it's a private LTE SIM only. It will not connect to Verizon, AT&T, T-Mobile, anything like that. There's no partnership at this stage of the game right now to federate that authentication. What does a SIM contain? Real quick, it contains asymmetric cryptography keys. It does not contain identity, it's just the keys. So when you're provisioning a SIM, you're mainly provisioning PKI. You're provisioning keys. A SIM is really just an encrypted secure container for file structure and holds multiple files. Those files can include some things for LTE like your home PLMN, which is primary land mobile network, which is essentially, hey, which operator? Each operator has an ID that contains the country code and the operator's unique ID. Which one is mine that I should connect to? Which ones are equivalent to mine? So if I go out of country and I need to get service, which ones should I look for and connect to? And then which ones are roaming PLMNs, which potentially are my last resort? Because typically the operator then needs to pay a back-end charge to get roaming data on a different carrier's network. It also includes the device's identity, or the IMSI, which uniquely identifies that SIM and that device to authenticate to the network. And then it has a whole bunch of other files for like your phone book and service dialing for operator service numbers, SMS parameters, all sorts of things. Question?
Is it possible?
Yeah, Sean, and then I'll get you, Heather.
Is it possible, let's say, hey, I got my CBRS set up over here, and then let's say a mile down the road, I got to run the office, completely different installations, but I want to roam onto their network also. Is there a way to share that information?
So the question is, if I have two private LTE networks, could I enable roaming between them? Yes, you would be programming your SIMs and your subscriber management system with an equivalent PLMN or a roaming PLM with the other network. So you could have federation. Let's say, one of the interesting use cases is like equivalent to EduRoam in higher ed. You could do very similar with equivalent PLMNs and roaming PLMNs, program those into your SIMs, and you can actually update SIMs with an update profile. I don't know if you've ever gotten one on a carrier network. Hey, update your SIM profile. Your operator's pushing a new profile down. You can do that dynamically so that you could deploy them today. Hey, they came online. We want to push out their ID so they can roam onto them. I could push that out and update my clients to do that. Oh, hold on. I want to get to Heather first. Heather?
I was just going to point out that the scale of information always that combine that with the CPI programming into it indicates that only the user device is allowed to roam. So there's no way to put this information in the base station. So the CBRS station cannot roam, so it cannot push.
Yeah, so the question was, this is UE or user endpoint specific, not infrastructure or CBSD, right? There's no concept of roaming for infrastructure eNode Bs. As in what? Yeah, I mean, this is purely a client roaming situation, yeah. Mike? Oh, sorry, Jim. So the question is roaming PLM is authenticated. Yeah, so there's a roaming relationship. There is an actual tunnel between one packet core, called a serving gateway, back to the originating home PLMN operator's packet core. And yeah, everything gets tunneled back. We went over types of SIMs, just form factors. There's removable SIM, eSIM, which is embedded. It's on the motherboard. And then, so the thing is the form factors come into play when you think about if I do want a device that needs dual SIM capability to be on both a private LTE and a carrier's network, what are my options? The big thing to note is that eSIM, you can only deploy one to a device because there's one eSIM module on the motherboard of a device. You can only deploy one profile to a device. So you cannot deploy multiple eSIMs to a device. So if you're doing dual SIM, you can do 2 physical SIMs if the device supports it, 1 physical, 1 eSIM, or 1 physical, 1 iSIM, for instance. So your dual SIM options are typically 1 physical, 1 eSIM, or 2 physical. And then you'd set one as your primary, so whichever one needs to be your primary, just think about, which one you want to be physical versus an eSIM. So for right now, like we've done a lot of testing on our stuff with, since we only support physical SIMs right now, moving the carrier to an eSIM, putting in a physical private LTE SIM, and then you can get dual SIM capability, so you don't necessarily roam between the private LTE network to the operator. You're not federating authentication. You just have authentication to both, and then the handset or the device itself has logic on which one it wants to connect to based on its signal quality, and it can fall back. And it can have a primary for data and a fallback for data. So you don't necessarily need carrier roaming if you do a dual SIM type of setup. And so, there's a couple of use cases. Travel, international, you might want a secondary SIM. Multiple subscriptions, which is the private and carrier within the same location. And then you might want, constant coverage if you're going in rural areas. You might want, hey, they have a coverage gap on one carrier. I want a secondary carrier for that area that covers it. Configuring dual SIM on a smartphone. You can do it on iPhone, you can do it on Android. Just a matter of popping in the SIM, going into the settings, and selecting, which one's gonna be your primary and secondary for data. And it's as simple as that. We're working actively with Apple and Google and others to work on their selection algorithm of which one they connect to and when, because right now you will have a break in service. It's very interesting if you're going from a secondary SIM operator into your primary, that transition happens very quickly. Because when it sees the primary, it wants to switch to its primary right away. When you're going the reverse, primary to secondary, it tries to hold on to that primary for as long as it can. So sometimes you'll get a break before it finally times out and triggers to go to a secondary, because it wants to be more conservative and stick to the primary. So we're talking order of magnitude of maybe not noticeable going from secondary to primary operator. Going from primary to secondary, you're probably looking at, right now, tens of seconds for it to figure that out and switch. So it's not horrible, but it's definitely not seamless. That's all the operating system manufacturers through the handsets and the devices, yep. It's their algorithm to select which network to connect to. Yes, it will change over time. They're actively working at improving those algorithms. There's a list. When you get the slide deck, you can look through here on what devices are capable of CBRS today. This is more reference material, so there's tablets and smartphones out there. More smartphones that I didn't mention, like LG has one, OnePlus has a couple. There's dedicated embedded devices for specific use cases, like bridges, cradle point routers, Sierra Wireless bridges and modems. You get into more industrial manufacturing type use cases, connected vehicle type use cases where these become important. Video recording solutions for security purposes. Yeah. So that's on CBRS planning from predictive through live measurement and devices and all that. Brief overview of the CPI program. This is going to be really quick. You're going to get access, like I said, to the CPI training program. So Salona has, as part of you attending this deep dive, you will get an email from Federated Wireless after the conference with access to the CPI training program. That's normally a $600 training program and certification. You get it completely free for attending, so definitely go and take advantage of that. It's usually about 6 to 8 hours worth of content to go through, self-paced. You don't have to do it all at once, but I would recommend just sitting down one day and doing it. It's an online certification exam, and then you're done and you're certified. So definitely take advantage of that. It's all online. They have multiple different courses. You're going to get access to the one that kind of contains all of it. So they have broken down different components if you're coming in at a different, point in your career and need to catch up or something like that. The CPI, yes, the left-hand one. You get the full program that you'll have access to. That includes 5 different modules. So the first module is on CBRS service in general. The second module is on the spectrum access system and all the protocols that it integrates and that it implements to facilitate the service. You'll have module 3 on working with the CBSD, which is again the radio eNode B side of what do I need to do to install and register a CBSD. Module 4 on working with the Federated Wireless Spectrum Controller. So that's their SAS that you integrated with. There's some manual ways to log into their Spectrum Controller, play with things, not just integration from a CBSD perspective. You can go in and do some things manually to look up Spectrum stuff in their system. And then Module 5 on actual certification, and you'll take an exam and then you'll be certified. So again, each module is about an hour to 2. In total, you're looking at probably 6 to 8 hours to go through the course. Definitely worth it. It's not hard content. You're sitting through this, it's probably, I'm going to go into LTE content that's much harder to understand than what you're going to go through in this. So take 6 hours, go do it one day, get certified, have fun. Well, not fun, I don't know. I took it. It wasn't fun.
Did you pass?
I did. You only have to get like 70%, so it's not like it's, challenging. Okay, cellular stuff. Who has any familiarity with 3GPP or LTE protocols? He does. I have one. Anybody else? Jim? Okay, good. So this is going to be an introduction. We have 10 minutes, and we could probably overflow to tomorrow. So why don't I do this? I've got probably about 10 minutes on cellular background on the standards organizations and the history. We'll break there, and tomorrow we'll dive into LTE before we get into hands-on. I think we have enough time tomorrow. We gave plenty of time for the hands-on tomorrow, so I think we'll cover LTE protocol tomorrow for about half hour, 45 minutes, and then we can jump into hands-on exercises. How about that? Sound like a plan? Okay. Organizations that you need to worry about. ITU and 3GPP. So just like we had WinForum and CBRS Alliance for the CBRS spectrum, from an LTE protocol perspective, you need to know about the ITU and you need to know about 3GPP. There were some other organizations back in the past, like 3GPP2 for CDMA stuff. Don't worry about it. Not relevant today anymore. ITU is responsible for global spectrum coordination, so worldwide. They have a conference every 3 or 4 years, where they go through and do alignment and proposals for, hey, what's upcoming? What do we need to plan for on a global basis? So they held one and they talked about, upcoming 5G recently. And then what they do is the technical standards are all defined by the ITU. The 3GPP is not a standards organization. They're not like the IEEE. They're not like WinForum. They do not develop technical standards. They develop what they call technical specifications. So the difference there is ITU sets the requirements. 3GPP says, here's how the specifications that we propose to meet those requirements, and then the ITU approves them. So ultimately, the standard is ITU. The 3GPP is just a specifications and proposal committee. It's very confusing. When you look at their stuff, it looks like technical standards. It is technical standards, but they're not a technical standards organization. They don't actually, they aren't responsible for approving it. It's the ITU. Make sense? Clear as mud? Okay. The 3GPP is broken down into working groups and task groups. So there's 3 primary working groups. There's the RAN, which is all the radio side stuff. There's the core network and terminals, which is like all of your core stuff. And then there's the service and system, which is like the overall architecture, security, and things like that. The thing you should know about this is everything gets approved through the one on the right-hand side. That service and systems aspect working group is the primary working group. It has to approve all the specifications from all the other groups, from the other 2, and from all the task groups within them. So the main body here is the right-hand side one. And then within those, you have task groups for different aspects of the protocol. So, RAN working group 1 is for, layer 1 PHY stuff on the radio. Working group 2 is for the MAC and layer 3 stuff on the radio side. And so you get, they break out into very functional task groups. The history of the generations of cellular service. So started actually prior to 1981. It's actually, cellular stuff goes back to 1947 actually, but I didn't put it on the slide because it was kind of irrelevant. But there were a lot of AT&T and FCC started to work on radio communications in 1947. And so there were a lot of like legacy proprietary, very, very limited use deployments between 1947 and 1981 by AT&T for very specific radio communications needs that eventually evolved into the cellular standards. 1G, big thing to know is it was all analog. 2G really brought in digital voice, but it's still circuit switched. So, you know, if anybody's familiar with circuit switch versus packet switch sets up an end-to-end communication path that reserves resources end-to-end before in setup of a session. So with 2G, we actually started setting up, it's still circuit switched, setting up an end-to-end call, but we just used digital modulation, or digital instead of analog modulation. 2.5G started bringing in data service over that circuit switched path. Very, very low data transmission rates, like kilobits per second. This is where you get into like GPRS and CDMA starting to come around. 3G is really, you know, that's the one that really became widely known and popular for a data service network. In 1999, we had, you know, a couple of megabits per second in speed, and we had a breakout between different standards organizations implementing different technologies in different regions of the world. So we had 3GPP mainly in Europe doing essentially UMTS service, which is built off of GSM. And we had 3GPP2, which was CDMA-based technology being used in the US. So back in the day, if you're old enough, you probably remember, hey, I had a certain operator's phone. This wasn't, I couldn't take it internationally because it wasn't a GSM-capable phone. Yep, it was Verizon primarily. AT&T did GSM, so you could take some phones internationally, others you couldn't. There was a bifurcation in the standards completely. What's interesting, just a wrinkle, is that we always think of Europe being GSM, but that's really a 2G technology. For 3G, they actually did a version of CDMA. So we always think of, you know, US was CDMA based and Europe was GSM based. Well, for 3G, actually both were CDM based, just different versions, flavors of CDMA. It's very weird. And so then when you get, you know, Edge service was the UMTS 3GPP equivalent, and EVDO was kind of the 3GPP2 CDMA US-based equivalent. So when you remember those terminologies, just remember Edge was one, you know, EVDO was a data service from the other one. And then 3.5G, they just increased the speed. That's where you got HSPA. In the 3GPP world for the US, or for the 3GPP2 world, you got ultra mobile broadband. I think this is where you start to see the 3GPP taken over again. HSPA was much more popular. And when we get to 4G, Verizon was the one who did the CDMA 2000. They were the oddball. With 4G, Verizon went to the dark side with 3GPP and the LTE standard. And so everything kind of remerged. So that's why everything's kind of standardized again. You don't have to worry about which phone model, because essentially when Verizon decided to go back to the 3GPP version, the CDMA 3GPP2 version kind of just died off. So 3GPP2 is not a thing anymore. It's not an organization anymore. Nobody uses it. It's just historical reference. And then you start, so you go back one. 3GPP release 99 was 3G's original version. So you see release 99, and that means 1999, 3GPP's initial 3G release with UMTS. And then they started changing their numbering based on just incrementing numbers after that. And so you really get into release 3, 4. Release 8 was LTE or 4G. And the big thing there is they overhauled the system architecture. So you get into what's called system architecture evolution. And this is an all IP-based architecture. So prior to 4G LTE, you had stuff that was still not all IP-based. It was still potentially some circuit switched, legacy protocol based. They overhauled it completely and you get all IP. Some of the terminology in there is all IP network is the same as an evolved packet core. So getting into some of the terminology of if you see these, when you start learning LTE or learning the technology, these mean essentially the same thing. And evolved UMTS, terrestrial radio, or EUTRA, is just the exact same thing as LTE. It is the air interface for the system. It brought in MIMO, it brought in OFDMA, it brought in FDD and TDD options for the protocol. So if you are having paired license spectrum for frequency division duplexing, one frequency band or channel is uplink and the other channel is downlink, you've separated them onto different frequencies. Or you're doing TDD, which is what we're doing in CBRS, which is all on one channel. You're time division duplexing on the same channel, uplink, downlink within the same channel. Other big things there, release 10 brought in LTE advanced, higher speed, we get higher MIMO. We start to get carrier aggregation, meaning just like you have wider channels in Wi-Fi, we're starting to get carrier aggregation across multiple radios. And so each radio can have what's called a component carrier. So that can be, let's say in release 10, it was up to 20 megahertz. You can combine multiple radios, just like you have dual radio APs, you can have both radios operating together for carrier aggregation. So it's a little bit different than Wi-Fi on just how wide the channel is on one radio. Carrier aggregation in LTE is aggregating the bandwidth and capability of multiple radios that are hardware based. So if we have a 2-radio eNode B here, if we do carrier aggregation, both radios are looking as one cell with potentially 40 megahertz, 20 on each. And I'm almost out of time, but that's good, we're almost done. Let's see, what else is big here? This is mainly just reference material for you, so when you get the slides, you have some basis for reference. Release 14, 2017, we got band 48 defined. Band 48 is the CBRS band. So it was, 3GPP they incorporate every band that is supported and they have it in their specs. And there's, all sorts of different implications for that in the specs. Band 48 and the definition of that band came in 2017. And then release 15 and release 16 are going to be 5G stuff. Just so you know, when we talk release 15, we're talking 5G new radio stuff. Yeah, I mean, you get, the other thing you guys might care about is release 13, they started to do LAA stuff. Remember that? When that was a big deal. We might start to see it actually get deployment in 6 gigahertz, so it might come and affect you, but I haven't seen much of it yet. 256 QAM support. Yeah, I mean, they start to do all sorts of funky things with interworking with other technologies, starting with like release 12 and on. So, but this is just a snapshot. There's a lot of technical detail in all these releases that I'm skimming over, and half of it I don't understand, so I didn't put it on the slide. And then this is the last slide for today, and then we'll break. So I really appreciate your patience today going through a lot of slideware. Tomorrow we'll just do LTE and then hands-on, and we'll have a lot more fun, hopefully. This is just the capability of, based on cellular generation, what the peak data rate was, and for a macro network, what the typical download speed is. But again, take that with a grain of salt. That's a macro network under, typical loaded congestion in different markets and things like that. So you can see, yeah, with LTE, the speeds have ramped up quite dramatically. So LTE advanced, technically you can get almost a gigabit of raw data rate. So it's fairly equivalent to where 11AC is kind of at, depending on channel width. And 5G is going to take that to multi-gigabit, again, based on carrier aggregation and, combining multiple radios and multiple channels and millimeter wave and all of that. So. The question is AT&T's 5G evolution. That's actually LTE advanced technology. It's not 5G. So I think, same marketing tactics that you're used to as people want to claim something is the greatest first to market. Yeah, whatever. So, yeah, I'm happy to answer any questions after the session and take some more tomorrow. I think I'm out of time. I got to let NetBees set up.